So a question that kind of popped up in the last exercise is if we have the rational function y equals ax squared plus bx plus c divided by x squared plus dx plus e, can we have y prime of x equal to 0 for some x in the real numbers? So if you haven't had a go at this, I encourage you to, because maybe it's a nice fun exercise. I don't know. Or maybe you'll hate it. But exercises are good to do anyway. So yeah, pause the video and have a try at it if you haven't already. Okay, let's talk about maybe one way to approach it. So I guess the obvious way is to just differentiate it. And I've written out all the working here just because it's going to be kind of boring to watch me stumble over all my expansions and everything. But yeah, so we have y prime is equal to this thing here, just using the quotient rule, which needs to be equal to 0. And that means that the top part needs to be equal to 0. So expanding everything out, we arrive at this equation here. And then just more expansion, more expansion, more expansion, more expansion, more expansion, more expansion. And then finally we end up with this inequality down here, which leads to this inequality down here. And then finally we can divide everything by 4, which leads us to this inequality down here. So what we calculated is that the derivative of this rational function y, which has arbitrary real numbers a, b, c, d, and e, we can get the derivative equal to 0. Well, from here to here, we use the discriminant. We're checking if there's any x values, and there are only x values if the discriminant is greater than or equal to 0. And then from there, we expand it to arrive at this inequality down here. Now, I mean, just looking at it, maybe it doesn't look that helpful, just at an immediate glance. But then we can see that definitely it is possible for non-zero real numbers a, b, c, d, and e. Just for example, consider this lonesome c squared as a single term. So we can choose, for example, choose large c. And then once we've chosen a large number c, we can actually make this side of the inequality as small as we like. Can make this side as small as we like, letting a, b, d, and e tend towards 0. So we can choose them as close to 0 as we want. And so this side here will be really small, whereas this side is going to be large because we have a big value of c that has been squared. And then similarly, all the other terms would go towards 0 as well because they have a's, e's, b's, and d's in them. So that's just a quick way to see that, yes, there is at least one combination of a, b, c, d, and e that satisfies this inequality here, and therefore makes the discriminant of this quadratic equation greater than or equal to 0, and so therefore there are values of x which satisfy it, and therefore there are values of x for which y prime of x does equal 0. So we can have, I guess, maximums, minimums, or points of inflection for a rational function of the form ax squared plus bx plus c divided by x squared plus dx plus plus e. And of course we could chuck an f in there. It makes no difference because a, b, c, d, and e are arbitrary real numbers, and we can just divide them all by f anyway and get more arbitrary real numbers. So that means for these rational functions, you do need to check to see if there are maximums or minimums before you sketch them.